So the main important key roles I told here is that one is my turn on circuit, which means that my circuit is capable of turning on SCR. I don't have control to turn it off. I don't have control to turn it off. It has to turn off automatically. Okay, that's with the line commutation. Then I told you synchronize means the control pulses should be synchronized with the main supply voltage. Then UJT, unijunction transistor, is a special type of the transistor where it has got only one junction. One junction. This is suitable for maybe you are generating switching pulses for your SCRs, maybe timing delay circuit generations. There and all we use the UJT. Then relaxation oscillator means this particular circuit is capable of generating non-sinusoidal signal at its own by itself. That's why it's called UJT relaxation oscillator. It oscillates and gives the signal. Now, in this experiment, the block will be there, module will be there. Module will be there. The module number is this EC330-1. So we may use this lamp, the GLS lamp. What is GLS lamp? You should tell me. Then glass lamp. You should tell me. Then we don't use a transformer here anyway. We use some voltmeters, some patch cords and all. Very basic circuit because we hardly require some 2 or 3 wires to do the connections because in the module everything will be available. Everything will be available. So let us understand how my UJT looks like. These are the basic Viva questions, remember. When you see the UJT, the symbol of UJT is something like this. It is similar to my FET, field effect transistor, but not exactly. Some small modifications there. We know that arrow is pointing towards the base, which means that my base is N-type, base 1. When base 1 is N-type, base 2 is also N-type. Then obviously my emitter is P-type. You can see that emitter is a P-type semiconductor, P-type substrate, and base 2 and base 1, it has got the N-type. It has got N-type material. It's the main channel through which current flows here. Through which current flows through my emitter itself. The emitter is going to control the junction there. Then if you observe here, my P-type emitter is towards base 2 and away from the base 1 when you see this particular figure. Towards my base 2 and between base 2 to the emitter point, we have the resistance called RB2. Between base 1 to emitter, we have a RB1. Since my P junction is towards, or P type semiconductor is towards B2, RB2 is not same as RB1. RB2 is not same as RB1. RB2 will be slightly lesser than RB1. Slightly lesser than RB1 because of the distance variation. So RB2 will be lesser than the RB1 because of the channels. Then continuation to this. Now if you observe the simplified equivalent circuit here, we come to know that there are 3 terminals. One is the impedance control terminal, base 2 is the power terminal, and base 1 is a common terminal. Like how you write a transistor. In a transistor, we have a collector, emitter, and the base. The collector is upper point, the power terminal, and base is the control terminal, and emitter is a common terminal. In case of common emitter configuration, same thing. Collector and emitter is nothing but base 2, base 1, and my base itself is the emitter here. The names are different, not same as your transistor. And it's called unijunction as I told you because there is only one junction available here. Then, if you measure the voltage here at this particular point with respect to the ground point, this my base 1 is ground point. So my supply voltage, let us say the main supply voltage is VBB. From the B2 to B1, I applied supply voltage VBB. VBB is the main voltage. I want drop across my RB1. That we say VRB1. VRB1 is equal to the same resistance RB1 by the ratio RB1 plus RB2 times VBB main supply voltage. The ratio RB1 by RB1 plus RB2 is called eta. Eta, intrinsic impedance, or what you say intrinsic impedance ratio, eta. Eta is the ratio of RB1 by RB1 plus RB2. And VRB1 is basically voltage drop from the emitter junction point, cathode point to my base point. So I want drop over here, which is nothing but the main voltage VBB times RB1 by RB1 plus RB2. That is nothing but my voltage division technique. I just applied the voltage division technique. Then it's told that unijunction transistor or UJT for short is another solid state 3-terminal device. Okay, that can be used to generate gate pulses for this particular experiment. Timing circuits, we can generate a timing delay also, trigger generate applications. So these are some of the applications, but definitely we use this UJT as a switch, not as an amplifier. As you know very well that in the entire power electronics, all the semiconductor switches we use as a switch, not as an amplifier. Not as an amplifier. Next he says like diodes, UJT are constructed from the separate P-type, nothing but the emitter point, N-type semiconductor material, forming a single PN junction. The Viva question is why it is called uni-junction. It's called uni-junction because there is only one junction available between the P-type emitter and the N-type base points. So this is a special design. Then it's got vast applications. It's used for a timing circuits, pulse generation circuits, all of them. We are giving one a particular application of that. And this UJT I'm using as a switcher, no doubt about it. But the switching characteristics will be not same as that of the conventional FET because this symbol resembles FET. But there is a, you can see the emitter point, there's a bent arrow is there, a bent is there, and arrow is pointing towards base point, nothing but my base is neutral, I mean sorry, base is N type and base is also N type, the midpoint emitter is by P type, NPN sort of thing, but N and N are interlinked there, they are interlinked, which is going to offer the impedance called RB1 and RB2. Continuation to this. Then, as I told you, it is called relaxation oscillator. The very reason is that it is going to generate the non-sinusoidal waveform on its own, depending upon the RC elements there. This is the first circuit. How we should, let us see what the circuit will do, how the circuit functions. Now, this is a very simple circuit. This is my main supply voltage V, and these are the some RC elements. RC element whose time constant is R into C, tau is equal to R into C. This is my emitter point, this is my base 1 point, base 2 point. Now let us see how the circuit works. Now here very important thing is there are two kinds of voltages. One is called peak voltage. Peak voltage as a reference voltage taken here. Another one is called valley voltage of UJT. Peak voltage, valley voltage is also Viva question. What do you mean by peak voltage and valley voltage of the UJT? It's very simple. Peak voltage refers to something to your latching current of the SCR. In the SCR, you might have studied latching current above which my SCR turns on. Same thing, my peak voltage. When the emitter voltage approaches peak voltage, then SCR starts conducting. When the SCR starts conducting, capacitor discharges. Then, when the emitter voltage, nothing but capacitor voltage. Say when I say emitter voltage, nothing but the capacitor voltage with respect to ground point. This is my common point. When the emitter voltage is lesser than the value voltage, then then my switch will be turned off. That's something similar to my holding current. Holding current. You know, SCR what we say holding current. Latching current is I say 25 milliamps. Holding current will be normally one third of that, maybe some 7 milliamps. If my anode current is more than latching current, SCR turns on. If the anode current is less than holding current, SCR will be turned off. Same thing here also, but in terms of the voltages. If the emitter voltage or the capacitor voltage is more than the peak voltage of the switch, what you call VP, then the switch conducts. If the capacitor voltage or the emitter voltage is less than the value voltage VB, then the switch will be automatically turned off. Automatically turned off. That's what the reference shown here. This is a waveform across VE, nothing but your capacitor voltage. Correct? Nothing but the capacitor. When I say VE, other point is my ground potential. Now, we have given the supply, the current start flowing here, but the switch is off, current won't flow here. The capacitor starts charging. When the capacitor voltage approaches peak voltage here, immediately switch will be turned on. When the switch turns on, capacitor discharges. At the same time, main current flows here because switch is turned on. The switch is turned on, main current flows here. At this particular point, the discharging voltage of the capacitor, this area, is nothing but the voltage available across my B1 point to the B1 point to ground point, which means that we copy this area over here. This is a voltage available across my B1 or R1, the resistance R1. Then, what will happen at this particular point? Again, the voltage is going below value voltage. At that point, the UJT will be turned off automatically. Again, what will happen? Again, the resistance through this resistance capacitor starts charging. Capacitor charging. When the capacitor reaches the peak voltage here, obviously again the switch will be turned on. When the switch is turned on, capacitor discharging in this particular direction in this loop. When the capacitor is discharging, whatever the voltage waveform we write for the capacitor, The same voltage waveform, the area, same area of the voltage holds good for the voltage waveform across my R1. I'm just copying that. So VB1 voltage will be spikes. You can see some sort of a spike here. You will be getting spikes something like this every time. So this spike is suitable for triggering your SCR, turning on your SCR, which means that the voltage VB1, somehow you give to the SCR gate terminal, it will be turned on. It will be turned on at this instant. We got a delay here, you can observe. We got a delay here. At time t is equal to 0, I don't have a pulse of the VB1. After some time, I have a pulse. That is depending upon the RNC elements. RNC elements. If I put the resistance is 0, when I put the resistance is 0, what will happen? Immediately capacitor, what will it charges very faster. Because resistance is 0, it charges very faster. It discharges here itself. Then I get the pulse here. Got it? Then again, it charges, discharges very faster manner. Now whatever the time period of my capacitor is gone down, reduced. So I get the pulses immediately. Everywhere I get the pulse here. So the chances are there that I get the pulse at alpha 0 itself. At the midpoint only I get the pulse here. So that is depending upon the resistance that is there in my RC network. RC network. When the resistance is least, capacitor is very, very faster. At time t is equal to 0, only capacitor charges to peak voltage, somewhere here. And once the capacitor is reached the peak voltage, immediately the switch will be turned on. The current start flowing here. The main current flows here because I'm using my UJT as a switch. Then I expect the pulse here itself. My delay is reduced. Delay angle, firing angle alpha, depending upon the resistance. Depending upon the resistance, alpha is called a delay angle, firing angle, which is used to trigger the SCR. Suppose when I keep the resistance huge value, very high value, then you see the capacitor voltage will increases very slowly. Somewhere it will go, then it will discharge somewhere here. Then I get the pulse somewhere here. Then I have my firing angle is increased, delay is increased. That is depending upon the time constant of my RNC elements. This is my variable resistance actually. Once I set the resistance for a particular value, maybe 10 ohms or 20 ohms, I can say that the respective firing angle will be fixed. Fixed such a way that every 45-degree, my pulses will be giving to SCR, SCR will be turned on. So these are the basic circuit how my UJT will works. I'm not going to the main power circuit. This is my control circuit. UJT relaxation oscillator basically control circuit. I'm not handling power circuit as of now. So what and all we understood, when the emitter voltage is more than or equal to, greater than or equal to peak voltage, then only UJT will be turned on. When the VE is less than or equal less than VV, then what will happen? Switch will be turned off automatically. Then we can vary the firing angle alpha by varying the resistance available in the RC network. When the resistance is 0, the capacitor charges very faster to peak value, peak voltage. Then immediately I get the pulse, one of the pulse over here itself that is suitable to trigger my SCR at alpha 0. At time t is equal to 0 only I can turn on the SCR. When you keep increasing the resistance, obviously this particular pulse will be keep moving right hand side. I can set 0 degree, 10 degree, 20 degree, 45 degree, up to 180 degree I can vary. So in the experiment what we do, by varying this resistance, we are going to vary the firing angle and we see how the output DC voltage will be varied. It will be reduced. How it will be reduced, we see that. Okay. So this is the highlight of this particular circuit. Now we see the static characteristics of UJT, or otherwise is a plot of V versus IE. V versus IE. Normally, your UJT operates in the negative resistance region. Negative resistance. What is the basic property of a switch when you observe? Let us see before going to the circuit diagram. It's a plot of current versus voltage. I want to see the plot of current versus voltage, which is nothing but voltage across the switch and current flowing through the switch. I want to write that particular plot. And I put some connection supply here, some DC voltage, some resistance. Now, when the switch is in off state, what is the voltage available across the switch? Nothing but the supply voltage. Because the open circuit, my supply voltage say V in. the Vin is available across my switch when the switch is in off state. So my voltage is maximum when the switch is in off, but current is zero. That is why my point coordinates is along y-axis because current is zero. The current flow in the switch is zero. Then, when the switch is permanently turned on, voltage drop across the switch will be zero, current will be maximum. I get the point here. So my coordinates, when taking coordinates, is a whatever the voltage current is comma 0 here. Is comma 0, which means that voltage and current are here inversely proportional. But when you see the practicality, it won't switch in this manner. Some sort of a curve will be there here. Some leakage current, some drop across the voltage when you take. It's not exactly straight. I mean, y-axis, x-axis syncing there. I get some sort of curve like this. Okay, this is something like a negative resistance region, which means that when voltage is maximum across the switch, current will be zero, which means the switch is off. Or otherwise, when the switch is turned on, voltage is zero, current is maximum, ideal condition. This is the negative resistance region, what we say. Same thing holds good here also in the UJT when you observe. UJT characteristics go something like this, but I'm going to operate. This is my value, a peak point, and this is my valley point. In between these two, I'm getting that inversely proportional curve. Inversely proportional curve here, negative resistance region. This is called negative resistance region, which means that when the voltage is maximum, current is zero, and vice versa. So this particular feature is very much suitable for the UJT, for it to work like a switch, not as an amplifier. We never use UJT as an amplifier, but transistor can be used as an amplifier. But here, UJT will be suitable for to work like a switch forever, because this negative resistance region plays a vital role here. Continuation to this. Now we see the control circuit, which is going to generate the switching pulses in a proper manner for the power circuit. Power circuit we are not gone as of now. We are just understanding the control circuit only, what you call line synchronized UJT relaxation oscillator triggering circuit. Triggering circuit or the control circuit. This is my control circuit, which is going to generate the pulses, switching pulses that is required to be given to the gate terminal of the your SCR. So line synchronized. What do you mean by line synchronized? As I told you already, for a particular switch, say we have two switches. I'll give a small example. This is my switch 1 and this is my switch 2. Two switches are anti-parallel, and this is my supply, AC supply, and this is my load, this one particular circuit. I say this is switch 1 S1, this is switch 2 S2. What we expect, S1 should be turned on during positive off cycle, so that current flows from the source to load. S2 to be turned on during negative off cycle, so the current flows from the load to source in this manner, opposite direction. So positive off cycle through S1, negative off cycle through S2, because both S1 and S2 are the unidirectional switches. It won't conduct current in the opposite direction. S1 will conduct always current from left to right, always. Right to left it won't conduct. This is my left point and right point. Then S2 will always conduct current from right to left. So S2 will be suitable for the negative off cycle. S1 will be suitable for the positive off cycle. Now the problem is, for the switch S1, you are supposed to give the switching pulses during positive off cycle. For S2, you are supposed to give the switching pulses during negative off cycle. If you interchange, I am giving the switching pulses to the S1 during negative off cycle, no use. And giving the positive pulses to my switching pulses to the S2 during positive off cycle, no use. It is not synchronized. For which I should know what is my supply voltage pattern. When my supply voltage is attaining maximum, when it is zero, when it is zero, when it is negative maximum, I require the data, without which I cannot give the pulses here. Now what we do here, the AC supply we give it in the power circuit, same AC supply will be giving here also. I want to synchronize them. I want to synchronize control pulses I am getting over here should be synchronized with the BESCOM power supply. The same BESCOM power supply I am giving it to the power circuit. My power circuit, what I have written here, and control circuit, both should be synchronized. Otherwise, simply give the pulses somewhere else. There is no use, right? Now, let us see how the circuit works. Most of the part we have already discussed. So we have seen some resistance, variable resistance here, capacitor RC element, and some additional element here, resistance UJT, unit junction transistor, and some, this my PT. Okay, this is my pulse transformer which I am using here. PT is just for isolation here. So potential transformer is different, pulse transformer is different. Pulse transformer is just for isolation. It's going to generate the high switching pulses, and the irrespective of whatever the frequency you can go, it'll support you there. Okay. Now let us see how the circuit works. Here I am going to give the 230 volts. But what is my requirement? I have to generate a pulses, maybe VP somewhere at 5 volts. 5-volt pulses I have to generate. Now I need to step down the voltage. Here I don't want any step down. Now I use the diode rectifier. What the diode rectifier will do, when I measure the voltage from U point, it's written U here, U point to ground, I get the diode rectifier, bridge rectifier output voltage, nothing but the pulsating DC voltage I'm going to get there, because diode rectifier is going to convert AC to DC, pulsating DC. I got the waveform at point U to the ground. I get the output voltage which is positive in nature. Okay, pulsating DC. Then now I'm using a Zener diode here whose Zener breakdown voltage is 20 volt. We say normally whenever you want to buy the Zener in the market, you should tell what is VZ and PZ. VZ is the breakdown voltage. Above 20 volts, it's going to break. Means that it can handle only 20 volts. Then PZ maybe 1 watt is given here. It is a 1 watt Zener diode whose Zener breakdown voltage is 20 volt. Is 20 volt. Now, whenever you give the 230, 230 is my RMS voltage. Remember, 230 is RMS voltage. Then what's the peak value of that? Can somebody tell me what's the peak value as per Indian standards? My supply voltage is RMS. We say 230 volts available at the home. What's my peak value here? Maximum value. Can somebody answer this? What's the relation between the VRMS and Vmax? Vmax is equal to box, what are written, times VRMS. What is this box fill up? Anybody can answer? Basic question. Yes, please tell me. Root?
Root 2.
Correct. Okay, be confident enough. Who is this?
Pavitra.
Pavitra. Yes, good. So Vmax is VRMS into root 2, which means that V maximum for your house you are getting somewhere around 325 volts, roughly 325 volts, the maximum voltage that is available at your house also. Vmax is 325. But what is my requirement? I want to chop this to 20 volts only. So my Zener, when I put the Zener here, it's going to chop it to 20 volts only. When the voltage attains 20 volt here, it will be chopped here. It will be chopped such a way that remaining voltage will be drop across my this switch, this resistance. Here is 20 volt, then remaining voltage is 210 volt will be available here. Is available here is a 2 watt. See, whenever I say 2 watt, 33 kilo 2 watt, 2 watt means the moment I say 2 watt, it is going to draw very, very less current. Here 230 volts is there from the Bescom, right? You can draw 5 amps also. The moment I say 2 watt, it draws very, very less current. This is the opening point for your entire circuit. Opening point for entire circuit. It won't draw more than 2 watt. This circuit won't consume more than 2 watt. That's the meaning of it. So it can handle only 2 watt year afterwards. Year afterwards, right? So this current, how much it has to flow depending upon the wattage of this resistance. It's a 2 watt. Very small current will flow here. Because Zener also is 1 watt. It's not more than that. I'm handling everything with the watts only, small wattage. Then this current, what will happen? The 210 volt will be drop here. Remaining 20 volt is available here. Now this Zener is the source for the rest of the circuit. Zener of 20 volt is the source for the rest of the circuit. So it won't go more than 20 volt beyond this. Because this junction itself is a 20 volt. It's chopped to 20 volt precisely. It's a broke down at 20 volt. It won't conduct more than that. It's fixed to 20 volt now, Zener. That's the application of Zener. Now, for the remaining part of the circuit is 20 volt. Now current start flowing here. The current got a two path, path number 1, path number 2. Path number 2 current won't flow because my UJT is off. UJT is in off state. Now, depending upon this resistance 470K linear part, it's a potential divider. Depending upon this resistance, variable resistance, currents start flowing through the capacitor, capacitor start charging. Capacitor charging. When the capacitor voltage is greater than or equal to your peak voltage, then UJT will be turned on. When the UJT turns on, the main current flows through UJT through this primary winding of the pulse transformer. And because of induction, similar kind of a pulse will be generated in the secondary winding. If you observe here, this has got a one primary and two secondaries. Here also same pulse will be generated. But these and G1, K1 and G2, K2 both are isolated. So there is no common ground here. Maybe I can use this for one SCR, I can use this for another SCR. Independently it will work. But I'll be getting both at G1, K1, G2, K2, I'll be getting same pulse, no delay. Okay, both are going to generate same pulses at the same time because the core is common to both of them. The core is common to both of them. What are the flux produced from the primary winding linking to both two sets of secondary winding, and hence the pulses produced in the G1, K1, G2, K2 will be similar or same, almost same, right? Now, once I get a pulse here, that's what we have already discussed. This 20 volt is the reference voltage, or I can say almost a DC reference to my other circuit. Current start flowing here, depending upon the resistance. When the resistance is very, very small here, very, very small, even the small resistance is included here for some particular reason. I'll tell you why it is later. Now, capacitor start charging here. When the capacitor reaches the peak voltage, obviously the switch will be turned on. When the switch is turned on, current flowing through my primary winding of the pulse transformer, so that whatever the pulse here shown here is a waveform across my X point. So waveform across my X point. So every point is given notations. So this is my U point where I get this waveform. This is my V point across zener, I get this waveform. This is my W point wherein I'm going to get these pulses. I can measure all of them using CRO, power scope, or a conventional scope. This is my X point across my primary winding of the pulse transformer. I am getting this waveform. I can check all the waveform. I can write in the graph sheet all these waveforms, right? So next continuation to this. Similarly, I put my resistance very, very huge value. I put in complete cut-in. Now restart is a cut-in cut-out. I put the entire resistance of 470K. Then current start flowing the capacitor very, very slowly. Very, very slowly, so that capacitor voltage may increase somewhere here, reach peak value somewhere here, then it will start discharging. So at that particular point, whatever the area available here, so I'll be getting one small pulse here. So I got a huge delay here, huge delay because my resistance is huge and the firing angle is increased. So the resistance is proportional to your firing angle alpha, proportional to firing angle alpha. So alpha is called a firing angle or a delay angle or a triggering angle. Why it's called delay angle? After this alpha only, the switch starts conducting. This pulse is available at alpha, maybe 10 degrees or 20 degrees. After 10 degrees, the switch will be turned on. This switch, it is not shown here. The switch is SCR switch, which is there in the power circuit that we see later. This is only my control circuit. Okay, so let me come from the beginning. The 230 volts, 325 peak value is connected to the bridge rectifier. The bridge rectifier is going to rectify the signal and give the pulsating signal. So voltage across point is a pulsating signal with respect to ground point. Then we have a zener and then this resistance whose rating is only 2 watt and 1 watt, which means that hereafter current flowing is very, very small. Then what is my requirement for my control circuit is only small voltage of 20 volt. So we provide a zener whose zener breakdown voltage is 20 volt and 1 watt. So the 20 volt will be available from this junction to this particular junction. Remaining voltage drop will be across my 33 kilo ohms 2 watt resistor. Then for the remaining portion of the circuit, only my voltage available is only 20 volt, not more than that, because this particular junction is fixed to 20 volt, which is nothing but the zener breakdown voltage. Then current start flowing through this element. Here current won't flow. The reason is UJT is off state. UJT in off state. Current start flowing through the resistance and then capacitor. When the capacitor voltage nothing but point W to the ground. When the capacitor voltage or the VE or VC is more than or equal to peak voltage, then the UJT will be turned on. Once the UJT is turned on, current start flowing through the primary winding of the pulse transformer, potential transformer, pulse transformer, which is going to generate the pulses. Then, then definitely at the same time, secondary winding side, we can expect a similar kind of the pulse here. One pulse is shown here. So the small delay of firing angle alpha is there here. Why got the delay? Because that particular time my capacitor is charging. I'm getting delayed, very small delay because the capacitor is charging at that time, which is not reached VP so far. Not reached VP so far. Then, once switch is conducting, then the capacitor discharges through my switch itself. Through my switch itself. So the remaining portion of the capacitor, this portion I'm talking about, this portion we can copy as it is for your Vx. As it is for your Vx, right? So this process will continue. I'll be getting a sequence of pulses here, and generally for SCR only one pulse is sufficient to turn it on. Remaining pulses will be there. It's redundant but not required. But why we have so many pulses? That's separate theory is there, we see later. But we have a relaxation oscillator which is kept on generating these type of pulses on its own depending upon the RNC elements. Depending upon the RNC elements. Next question comes, why this diode is there here? Can somebody answer? Why we normally put diode across relay coil or a pulse transformer coil or any circuit? We put one diode there for a coil. Why we do so? We say
Freewheeling.
freewheeling diode. What's the function of this? Correct. Perfect. You are perfect. What's the function of this freewheeling diode? When the diode will conduct?
When the inductor discharges.
Correct. Yes, you are right. Which is something like this. In entire power electronics, whether it's maybe inductor or capacitor, if we talk about inductor, it has to energize, de-energize. You should use the word, last as I told you, na, energize, de-energize. You should reset otherwise. Reset it. Then only it will charge freshly, it will energize freshly, capacitor, inductor, right? Now what will happen here? When the switch is turned on, then inductor is energizing here in this particular path. This is my path. Already the current is flowing here. The capacitor reaches the peak voltage here. It starts discharging now through my switch. Now, this is a path available here for the inductor to energize. Then, once my capacitor voltage is reaching the value voltage somewhere here, then the switch will be turned off. When the switch is turned off, whatever the energy available in the inductor will freewheel in this manner, and where the power is dissipating, this primary winding has got both resistance and reactance, which is not shown here. Every coil has got resistance. The power will be dissipated in the resistance of the coil itself. Coil itself. Again, it will energizes freshly when the capacitor voltage reaches peak voltage during second cycle. So that is why we have the freewheeling diode across the coils to ensure that your coil has to reset when the energy is not fed to that, which means that energy all in the coil will be dissipated in the resistance of the coil itself. Again, it will be coming for the circuit part as a freshly to energize in a fresh manner. That's the basic idea here. Diode is for freewheeling to reset my coil, to reset the energy of the coil. Then this is my circuit where we come to know that my resistance variation, this resistance variation is proportional to the firing angle alpha. Alpha is a firing angle or a delay angle or a triggering angle. What is the term? We say technical term. We say as far as your SCR is concerned, firing angle, delay angle, triggering angle, which we these pulses we give it to the your gate terminal of the SCR. Gate terminal of the SCR. So this is my SCR circuit. So this is my anode, cathode and gate terminal. To this gate terminal I can give these pulses with respect to cathode, then we can turn on the SCR. Okay, any doubts here? The control circuit is concerned. Pavitra,
Sir?
can you please explain the circuit in a very simple manner by seeing the waveform? You try, no problem. Tappadra paragla.
Yes, sir. First,
Please.
the supply that's given normally to the circuit is given at the terminals A and B, and
Correct.
there's a bridge rectifier there. And
Correct.
after full wave rectification,
Correct.
there's the waveform is seen at point U, and
Perfect.
then um, this goes like it come the same voltage appears across Zener diode, and it's chopped off till 20 volts, and
Correct.
the waveform is seen at V, and then
Correct.
um, and
So
then
we
what?
got a 20 volt across the zener. Where is the remaining 210 volts available then?
across the resistor R1.
Yes, correct. This is a Viva question. Why the resistance is there? They will ask you. This is just to balance your voltage across my this particular loop, wherein 20 volt is a drop across the inner, remaining voltage will be available across the resistance. This for the balancing my voltage, right? Continuation. Yes, please.
Uh, and then when the same voltage appears across the point W, which is
Correct.
nothing but the emitter of UJT.
Hmm?
And then when this voltage keeps on increasing, the capacitor charges
Yes.
at E, and then when it reaches the peak,
Correct.
it again discharges, and
Correct.
the switch, it acts as a switch, and then
Yes.
this voltage will be seen across X,
Yes.
and across the isolation transformer, across
Yes.
G1 and G2, there will be pulses generated.
Yes, G1, K1, we have a pulses. G2, K2 is another independent pulse which we are not using. We use only G1, K1 for the one of the SCR to turn on. The G2, K2 we can use for one more SCR to turn on. Yes, good. That's good. Okay, hope you understood. Ramesh, Aditya Ramesh, Ramesh, Aditya Ramesh, Aditya M. You can unmute.
Yes, sir.
Yeah. Can you repeat the same thing again?
Uh, the supply voltage is given at A and B terminals,
Yes.
which is being rectified by the bridge rectifier circuit, uh, and the voltage will appear across U,
Yes,
and
correct.
next the Zener diode chops off the high voltage to 20 volts,
Yes.
and
Correct, you are right. The potential from V to ground is 20 volt now because inner is broke down at 20 volt exactly. It's maintain the 20 volt forever. V to ground, correct. Then what will happen?
then the voltage gets dropped across the resistor R,
Yes,
uh, and the voltage appear across V.
yes.
So
So
this
how
voltage
many
comes to the point.
how many paths are there for current to flow here? Two paths are there, right? So this is a
Yes, sir.
path one, this is a path two. Which path current flows now?
Now it
Path one.
flows path one.
Path 1. Path 2 current won't flow. Why? Why the current won't flow in the path 2? Because UJT is
You, uh, you
off.
can
UJT is off.
off.
Correct?
Okay.
Because I am not given any pulse here, right? UJT is off.
Yes,
Current
sir.
won't flow. Current cannot flow here because UJT is open. Now, tell me, continuation. When the capacitor voltage is more than particular value,
Uh, the UJT will be switched on. Uh, so the voltage will appear across. So the capacitor charges.
yes.
Uh, and the voltage will appear when the voltage at W is less than the VV.
Okay.
The capacitor discharges.
No, reverse. When the capacitor voltage is more than peak voltage, then switch will be turned on. UJT will
Yes,
be
sir.
turned on, so the current start flowing to the primary winding of the pulse transformer. When the capacitor voltage is less than valley voltage, which is shown here reference, valley is almost zero only, so less than valley voltage, then the capacitor will be turned, the switch will be turned
Off.
off, so that the capacitor, now what will happen when the capacitor voltage is more than the, capacitor try to reach the peak voltage, correct? When the capacitor voltage is greater than peak voltage, this will be turned on, then the discharge takes place, right? Discharge takes place, the capacitor start discharging. Same time, the main current will flow through the path 2 because which is turned on. Which is turned on. And again, when the capacitor discharging reaches value voltage, which will be turned off. Correct?
Off.
So thereafter UJT will be turned off. Further current won't flow there. That's why we get these type of pulses. which is nothing but the discharging area of the capacitor, correct? Discharging area of the capacitor. Okay, Aditya, thank you. Okay, continuation. So this is nothing but the discharging area of the capacitor. These are used as a switching pulses. Now we go to the power circuit. This is my power circuit. Okay. Now this transformer normally we don't use. This is a 1:1 transformer. We are not going to use in the lab also. Directly we give the supply to the your one switch and one load. Nothing but the GLS lamp. One load. Right. So this is similar to my AC supply and then switch, unidirectional switch, and then maybe a bulb. I can use a bulb here. This is my simple circuit. And we know that SCR conducts only in the one direction, which is unidirectional. The moment you give the gate pulse to this SCR will be turned on and then current start flowing. When you give the gate pulse, that is depending upon the your resistance available here. When the resistance is least, capacitor charge is very faster to the peak value. I get the pulse here itself so that the same pulse will be available to the SCR. It will be turned on at alpha 0 itself. Nothing but my output voltage, input voltage will be similar. So there is no any change, there is no any chopping. Now we see this particular circuit. Now, when we give the pulse at alpha, which is maybe say for example 45 degree, at 45 degree we give the firing pulse by keeping the resistance some value. At alpha I have given a pulse here. At this point I have given a pulse here. The moment I give the pulse here, then SCR will be conducting. When the SCR is conducting, the supply voltage will be available across my load point. So till from 0 to alpha, the load voltage is 0. Load voltage is 0. At alpha onwards, the switch is conducting so that supply voltage area, this area will be available across my load, which is not a full off cycle. Some portion is chopped there. Why it is chopped? Because switch is conducting only at alpha onwards. Only alpha onwards switch is conducting. Till then I don't have any control. Till alpha, the circuit current won't flow. Circuit current won't flow because switch is in off state. Switch is in off state. Very simple thing is that if you take this area, this particular what is VAK drop across my switch, which means that I put one CRO here across my A and K point. I just connect a CRO. I'll see what's the waveform I'm going to get there. Since switch is open, the supply voltage will be available across switch. This is nothing but the area available across the switch. The moment switch is turned on at alpha, the drop across the switch will be 0. The switch is 0. That time, this is work like a wire connecting my supply to load. So the supply voltage is equal to load voltage. So the remaining area of my sine wave will be available here. Negative off cycle, current won't flow because SCR won't conduct in the reverse direction. It won't conduct in the reverse direction. So that entire supply voltage will be available across my switch, which is open. Since my switch is open, entire supply voltage will be available across my switch. This is my open points. Switch is not, it won't conduct during negative off cycle even though you the pulses there. It won't conduct. Current won't flow in the opposite direction. The SCR. So SCR is open, which means that my circuit will be something like this: AC supply, and then open points, and then my load. When I put a voltmeter here, it show the supply voltage itself because open point. Current won't flow here. Current won't flow here, but the supply voltage will be available across my switch which is open. So that is the reason during negative off cycle, supply voltage will be available across my switch because it is open. Then at 2 pi plus alpha, 2 pi plus alpha, somewhere here I give the pulse here again, one more pulse here for the SCR. The moment I give the pulse, SCR will be turned on. When the SCR is turned on, I get the input voltage, output voltage similar. Same thing like this. Similar. This process continues. Suppose I keep the resistance in the UJT circuit very huge value. Very huge value. Let us see what kind of waveform we get. So when I keep the resistance very huge value, my firing pulse or triggering pulse from the UJT circuit will be available somewhere here. Because there's a huge delay because capacitor takes more time to reach the peak value. Then what type of waveform I get is till then the SCR will be off state till here I'll be getting the supply voltage same as that of across my SCR. At firing angle alpha, here onwards, I'll get the remaining portion across my load, because at this point I've given the firing angle. I can vary firing angle from 0 to 180 anywhere, so that the supply voltage waveform will be chopped. It will be chopped, which means that simple way I tell you. Suppose you have a supply voltage here, positive obstacle, anyway negative obstacle won't come to the picture. Suppose if I give the firing angle here, alpha, I get the waveform like this. If I give the firing angle here, I get the waveform only here, this portion. If I give the firing angle here, my output voltage will be available only here, very small. Whose average value will be least? Least. I get the area only this much area. Remaining portion of the area will be available across the switch, because switch is not conducting till that particular point. This is the waveform across the switch. This is my firing angle alpha, which is 170 degree. 170 to 180 only, I'm allowing the current to flow. Only remaining portion will be available here. That is the way, it's simple to say that my voltage drop across switch, voltage drop across load, if I add, I get back my sine wave. Because supply voltage is equal to switch voltage plus load voltage, even instantaneously also. Any instant you see, my supply voltage is equal to your drop across my switch plus drop across my load at any instant. So while writing waveform, very simple idea is that add your supply volt, I mean yes, add your switch voltage and load voltage, I should get back my sine wave. Just see. So here are some area is there, remaining portion is there. I got the positive area. Here I don't have anything across load. Here I have a negative area. Add them, I get negative area. So I get my supply voltage. So this is how the circuit works. By varying the your resistance available here, whatever the resistance available here, by varying this resistance, that is 470k pot, you can vary the firing angle. And you should remember that resistance of this pot is directly proportional to the firing angle alpha. Firing angle alpha. More the resistance, more firing angle, I get less voltage, less output voltage. If the resistance is 0, if the resistance is 0, firing angle alpha is also 0, I get the pulse here itself. When I get the pulse here itself, so switch will be turned on at alpha 0 or a time period 0 itself. I get a complete full cycle will be available across my load, because I give the firing angle here only. When you give the firing angle here only, switch will be turned on here only. There is no drop across switch at all, because already turned on there. I'll be getting complete input voltage across my load like this. The maximum DC voltage I can get. When you take the average of this, I'll be getting the reference line somewhere here. This is my average value of this particular area. Okay, so simple to say, my very basic circuit is AC supply. I'm not using the transformer in the lab also. The switch and then load, nothing but the bulb. This is a simple circuit. Since it's not a diode, I have a control rectifier. So it depends when you are going to give the firing angle alpha value. So based on that, I'm going to chop the waveform and I'm going to produce the output accordingly. So that in that way, I can vary the area of my output voltage, which means that I can vary the RMS DC, sorry, I can vary the DC voltage of the circuit, DC voltage of the circuit. Okay. Now, what we do in the lab is that this is a half-wave control rectifier, because instead of the diode, I'm using SCR. That's it called control rectifier. Instead of SCR, if you use your diode, it's called half-wave rectifier. Because of the SCR, it's called half-wave control rectifier. What we do, we are going to note on the time period. So supply frequency F is equal to 50 Hertz as per Indian standards. So the time period T is equal to 1 by F, which is you are going to get precisely 20 millisecond as per Indian standards. So my time period is 20 millisecond every time. It's 20 millisecond total time period. Small t is a variable t. So we just see what is it, how much time it has taken to generate the pulse. To generate the pulse. Maybe I may be generating the pulse somewhere here. I note down this what's how much time it has taken to generate this particular pulse point. Maybe 5 millisecond, say an example. Then I can calculate alpha, firing angle alpha based on this formula. Alpha is equal to t by small letter t by capital T into 180. Small letter t is 5 millisecond. Capital T is 20 millisecond. So into 180 degrees. So 5 ones are 5 fours are. So 180 by 4. 180 by 4 means 45 degrees. I'll be getting 45 degree. I can note down 45 degree here. And what is the VDC voltage available here when firing angle is very less? What is my DC voltage? I get a complete sine supply voltage available across my load, which means that I'll be getting more DC voltage. So since I'm getting only half wave rectification, negative obstacle, I don't have any output there. I'll be getting roughly on an average 50% of the 230 volts. 50% of the 230 volt, which will be somewhere around 110 or 120 volts I'll be getting here. Practically I have to verify using this formula. There's a derivation for this. The DC output voltage is given by V max by 2 pi 1 plus cos alpha. Let us say my alpha is 0 here. Alpha is 0. When alpha is 0, cos 0 is 1. 1 plus 1 is 2. My formula is 2 V max by 2 pi or V max by pi. V max by pi. V max is 320. Pi is 3.14. 320 by 3.14 roughly 100 volts. I'm telling very rough calculation. Roughly 100 volts. Which is satisfying there. I tell you once again. Let us say my alpha is 0. When alpha is 0, I told you that I am going to get the output voltage, something positive obstacle I get the waveform, negative obstacle I won't get it, again positive obstacle I get the waveform, something like this. What's the DC content of this? So theoretically we have this formula. So my V max is root 2 times 230, I'll be getting 325 by 2 pi into alpha is 0, cos 0 is 1, 1 plus 1 is 2. 2. 2 ones are 2 twos are. 325 by 3.14. 325 by 3.14. Pi is 3.14152. Let us say 3.14 is nothing but 3.25 roughly. Then hardly I get 100 volts here. I mean theoretical. Practical also I told you more or less you will be getting 50% of 230, somewhere at 110 or 120 some value will be getting. So theoretical and practical we are going to match there. Theoretically we are going to get the answer from this equation, and this is my DC voltage at the average value of the output voltage. Vmax is the maximum value of the input voltage. Alpha is the firing angle which is depending upon the resistance in the control circuit. Likewise, we vary alpha from 0 to 180 and we note down all theoretical and practical value. We compare them. It more or less they'll be same. Some 5-10% error will be there, but more or less they'll be same. Why the error is because of the drop in the wire, drop in the switches. We are not considered because the equation whatever you have derived here is a ideal equation. This ideal equation is not a practical equation where we consider resistance of the wire, resistance of the switch, all those things we are not considered. It's an ideal condition. So some 5 to 10% error will be there between these two. No problem. It's acceptable. It's acceptable. Okay. Now, this is the T small t capital small t we get from the CRO. So I'll show in the CRO how to calculate the time period. Because of the time division technique, time division knob will be there. By seeing the time division knob and we just see how many units it has taken here. Maybe somewhere I'll show you how many units it has taken here. That units you multiply with the time division knob and we come to know what is the actual time period here. This is small letter t variable. Small letter t variable. Capital letter T is the time period of the one full cycle. Nothing but t, nothing but 1 by f is 20 millisecond fixed. It's not changeable. It's a fixed for the supply. Only the small letter t is variable. We are going to calculate and note down all of them. Right? Then this is the first part of a control rectifier, but my output voltage is very less, 50% only I am getting, but I want almost a 230 volt DC. For that we use this one more circuit, what you call full wave control rectifier. Full wave. Instead of that bridge, I use the 4 diodes. When I use the 4 diodes, what will happen? At the point A or point U, I'll be getting the pulsating DC like this. This is my supply voltage of 325 peak. 325 peak. Then, now what we can do, since the voltage available here is pulsating DC, you start giving the alpha here. Suppose this alpha is 45 degree here. Then this point is 45 plus 180. This alpha. So that's what we call pi plus alpha. And this point is 2 pi plus alpha after one cycle. like that. For every obstacle, I keep adding pi there. Alpha, pi plus alpha, 2 pi plus alpha. Every point, I'll be giving the pulses to a SCR, so that SCR will be turned on at every alpha, pi plus alpha, 2 pi plus alpha. Then what is the voltage waveform I'll be getting here is that this portion will be available there, this portion will be available there, this portion will be available there. Before that, we didn't have the negative obstacle. Now we have some addition there. So it will be, I'll be getting something like this. We see the waveform next. Now I use the diode rectifier circuit to convert the AC to pulsating DC, so that I don't have a problem. This SCR will conduct both during positive off cycle and negative off cycle of the supply voltage. Because negative off cycle I have already inverted using diode rectifier. SCR will conduct during negative off cycle also. Current will be always flowing in the one direction only, unidirectional. Negative off cycle also current flows in the clockwise direction. Positive off cycle also current flows in the clockwise direction. Let us see the circuit diagram and its waveforms. Once again, I have written the circuit diagram and the waveforms. Now, you observe very keenly that we have given the firing pulses at alpha, then pi plus alpha, 2 pi plus alpha. Everywhere we are giving the pulses using the control circuit. When we do so, SCR will be conducting during positive off cycle. So the output voltage will be available here, and negative off cycle also output voltage will be available here. So what is the path for the positive off cycle? It flow through D1, SCR, load, D4, back. So negative off cycle, what will happen? Current start flowing through the D2, SCR, load, and D and back D3 here. So this is the path. This is a Viva question. Remember how the current flows. You tell me. So positive off cycle D1, SCR, load, D4, back. So this particular area I got it. Negative off cycle, current flow from B to A, right? B to A. But the moment it comes here, D4 is reverse bias. It comes through D2. Same SCR. Load. D3. D3 back to point A. It starts from B, terminate at A during negative off cycle. This you have seen student won't answer even after 3 or 2 months. When you ask some question how the current flows, they do not know. Blindly they tell. No, you should understand how the current is flowing. So it's through point A, positive off cycle, A to B, right? A to B is a positive off cycle. D1, SCR, load, D4. So D1, D4, thyristor 1. That's what written there. Negative off cycle, B to A. Now it is B to A. From B you start. B to D2. That time D4 and D1 are reverse biased. D4, SCR, load, D3 back to A. So D2, D3, you are T1 only. Every time T1 only. So once we chop the waveform at this particular point, remaining voltage will be available across my load. As I told you already, when you sum it up these two waveform, I get my supply voltage which is pulsating DC. Because point A is pulsating DC, it's not a pure DC. Pulsating DC. When you add this with this, I get back my pulsating DC every time. That's a basic idea. Basic idea you should have. Okay, again what we do? We put one multimeter here. Multimeter, we note on the in the DC mode. So we note on the DC voltage. Here the voltage will be almost double. Almost 220 are we getting. Now my formula is different here. What's my formula? VDC is equal to V max by pi 1 plus cos alpha. What's the formula here? VD is equal to V max by 2 pi. Denominator we have a 2, which means that 50% we get there in the off control rectifier. In this full wave rectifier control circuit, my formula is V max by pi, not 2 pi, pi. Because of that, let us say my alpha is 0 here. Alpha is 0. Substitute alpha 0. When alpha is 0, my value is 1, cos 0 is 1. So I'll be getting 2 Vm by pi. Before it is a Vm by pi, now this is 2 Vm by pi. So Vm is basically 325. 325 into 2 is maybe around 650 volts by pi. Pi is 3.14152. So let us say pi is 3.25. Instead of 3.1415, I'll put 3.25. So I'll be getting roughly around 200 volts. 650 by 3.25, I'll be getting roughly around 200 volts. So maximum voltage, double the voltage compared to previous case I'll be getting here. Of course, instead of 3.25 put 3.14152, I'll be getting 220 volt also, roughly 210, 220 volt I'll be getting. I'm giving a rough idea. Since this particular equation has got a cosine term, when you write a plot of output voltage versus your firing angle alpha, I'll be getting cosine term waveform something like this. Sine term is starts from here. Cosine term is at alpha 0, I'll be getting maximum voltage. Correct. Put alpha 0, I'll be getting maximum voltage. Put alpha is equal to 90 degree. Cos 90 is 0. I'll be getting V max by pi. I'll be getting 50% of the actual value. 110, 115 volt I get. It's got reducing. Which means that when alpha is 0, voltage is maximum. When alpha is 180, what is cos of 180? Minus 1. 1 plus minus 1. 1 minus 1 is 0. So VDC is 0. So you should remember that output voltage is inversely proportional to alpha. Inversely proportional to alpha, but resistance is of the UJT control circuit is directly proportional to alpha. Very important points to be considered here. So alpha 0 I get full output voltage, but because at alpha 0 only I am giving the pulse to the switch, it will conduct at alpha at time period 0 only. So my input and output voltage will be same. I'll be getting full voltage. When alpha is 180, which means that I am giving the pulse somewhere the dead end. Till then, I'm not allowing the switch to conduct. That there is no power flow, so my voltage will be 0. So alpha firing angle and output voltage will always be inverse. This is a plot you should write in the graph sheet. So this is my DC voltage, nothing but output DC voltage versus firing angle alpha. Alpha is equal to 0, output voltage is maximum. And alpha is 180, output will be reaching 0. Alpha 90, I'll be getting somewhere 50% here, 50% of the voltage. So this is my cosine wave that you should remember. A cosine wave because my formula is VDC is equal to Vm by pi times 1 plus cos alpha. So everywhere we have a cos alpha. Here also we have a cos alpha. Here also we have a cos alpha. Only difference is in half wave control rectifier and full wave control rectifier. Here the only change is denominator part 2. Here is Vm by 2 pi, which means that 50% is gone there. Whereas here it is just Vm by pi. So it's a double the half wave rectifier voltage. So we tabulate this and then we have the we can write the graphs for all these things. Right? Any doubts you have? Do you have any doubts? Okay. Do you have any doubts, students? Okay. Thank you. I think recorded. If you have any doubts, you can see 1 or 2 times. If you have still doubt, definitely you can talk to me. You can discuss with me any doubts you have because all this.
Okay, now we will start with the conduction circuit connections waveforms of SCR turn-on circuit using synchronized UJT relaxation oscillator. Okay, this is the relaxation oscillator circuit and this is the firing circuit or the control circuit which we use to generate firing pulses. Okay, as I told, we are going to first we are going to generate the firing pulses. Now let's see the same circuit in the kit. Okay, this is the kit what we have in lab. This 4 rectifiers forms the rectifier. This is the Zener diode and this is the capacitor which charges and discharges. This is the UJT and this is the transformer, isolation transformer as I told. This is the primary of isolation transformer. These two are the secondary and tertiary windings of the isolation transformer. In the same kit we have 2 SCRs. Okay, now as I told, we will first do the connections, then we will check the waveforms at different points. Okay, the connections are very simple. The entire connections of the control circuit is already done in the kit. Okay, let's go back to the circuit once. Okay, if you check the circuit, this entire connections are done. This entire connections are done. The only connection what you are supposed to do is this part. Okay, and you need to provide the supply 230 volts. Okay, for supply 230 volts we have a plug pin. I'll show you that. Okay, this is the plug pin what we have. It contains two terminals. Okay, one we are giving to diode one leg, and another one we are giving to another leg of diode. And this is the connection what I told, from V to resistance. Okay, these two are the connections what you are supposed to do to check the control circuit. First we will check different waveforms at the control circuits. We will see the firing pulses. We will see how alpha can be varied from 0 to 180 degree. Then we will move on to half wave rectifier circuit. Okay, let's start with the checking of waveforms. What we have to do is just give the connections, give the AC supply, then short these two terminals, and let's switch on the supply. Okay, switch on the supply. Now we will observe the waveforms at different points. If you notice, we have connected 230 volt supply here, right? We have connected 230 volt supply here. So we need to use power scope to measure this waveform. Okay, this is the power scope what we have in lab. In AEC lab or in electronics lab, you have seen only this part of oscilloscope which measures voltage up to 20 volts peak to peak. But this oscillator can measure voltages up to 325 volts and 400 volts of peak value. And it is very important to measure waveforms using this oscilloscope whenever you are measuring 230 volts supply, or if you are measuring voltage across load. Okay, this is the bulb load what we have in lab. If you are measuring voltage across this load also, you are supposed to use this power scope. Okay, the usage of this power scope is same as the normal oscilloscope. The only difference is, instead of taking probe from here, you will be taking it from these two terminals. From these two terminals, we will be having the connections like as you had in multimeter. Using these two probes, we can connect wherever we want and we can measure the waveform. And one more thing to be noted is, here you can see in the oscillator, we have channel 1 and channel 2. This is y-axis scale for channel 1. This is y-axis scale for channel 2. This is the time scale for both the channels. While taking down the readings, how you are supposed to do is, you need to measure how many divisions the waveform is covering. You have to multiply it with this scale, then you have to multiply it with this scale over here. Okay, you can keep it either at 10 or at 100. For example, if your waveform covers 2 divisions, then 2 divisions into, according to this, the scale is at 1. So 2 into 1 into 100. I have given it to channel 1. So for channel 1, the scale what I have taken here is 100. So you need to multiply 2 into 1 into 100. So it becomes 200. Okay, like that you need to measure the values in the CRO. Now first let me show you the waveform of the supply. Then I will show you, first I will show you the waveform of supply. Then I will show you the waveform across the rectifier output terminals. Then across Zener diode. Then across capacitor. Then across the secondary of transformer. First let's connect it to voltage across supply. Okay, let's connect it across voltage across supply. So you can observe here the voltage waveform is seen. And you can check the ground level also. You can check the ground is proper. So this is the AC supply voltage what we have. Here if you note down the value, it's 1, 2, 3. It's covering 3 divisions, and the scale what I have taken for channel 1 is 1, and the scale what I have taken here is 100. So it indicates 300 volts. It indicates 300 volts peak value. The peak value of AC supply what we are giving is 300 volts. So peak to peak it's going to be 600 volts. Okay, this waveform you have to draw in the graph sheet. This is the first waveform we will be drawing in the graph sheet. There is a sinusoidal signal with 50 Hz frequency and the peak value is 300 volts. Now this supply we have provided across these two terminals. Now let's check the rectifier output voltage waveform. Okay. Now I am connecting across these 2 points. Okay, these 2 points are the rectifier output voltage points. Now let's see the waveform. Okay, the rectifier output is DC, so I am keeping it in DC mode. So this is the rectified output voltage waveform. The peak value is not going to change. Peak value is not going to change. Now this is the waveform. This is the second waveform that you are going to draw in your graph sheet. First is sinusoidal signal. Second is rectified output voltage waveform. Next, we will be measuring the voltage across Zener. Okay, this terminal and this terminal. Okay, this gives voltage across Zener. Now let's see how the voltage across Zener is going to be. Okay, the voltage across, in order to measure the voltage across Zener, I am increasing the scale. So you are getting a waveform like this. Here it is, how much divisions you are getting. You can note down the readings as well to plot the graph. Okay, the magnitude is going to be 1.4. Okay, if you check, it's 1.4 into the scale what I have taken is 0.2. 1.4 into 0.2 into 100. Whatever the value you get, around 1.2 into 0.2 is, sorry, 1.4 into 0.2 is 0.28, around 20, 28 or whatever the value you get. 28. That magnitude you have to take for Zener, voltage across Zener diode. Now let's see the waveforms across capacitor. Okay, this is the capacitor one terminal and this is capacitor other terminal. Okay, now this is the waveform of voltage across capacitance. Now if I change the time scale, now the time scale is at 5. If I change the time scale, okay, no need of changing the time scale, you can check it like this. This is the capacitor charging. This is the capacitor charging and this is discharging. Capacitor charging, discharging, capacitor charging, discharging. This is same as the waveform or the peak point. Okay, this is the peak point. This is the peak point and this is the valley point. Okay, when the capacitor reaches this voltage, UJT turns on. When capacitor reaches this voltage, UJT turns off. Okay, it's not necessary that you will get this many number of charging and discharging cycles in 180 degree. That depends upon your resistance value. See, now here I am varying this resistance. When I vary this resistance, this plot is going to change. The number of charging and discharging cycles per 180 degree will change. I am varying the resistance here. So the charging and discharging cycles will vary. While drawing in your graph sheet, it's not compulsory that you have to draw only 5 cycles or 6 cycles. You can draw as number as you possible, as many as you possible. And the one thing what you need to take care is, while drawing the next waveform, it should be synchronized. Whenever the capacitor discharges, that voltage will appear across the primary of the transformer, right? So this will be transformed to secondary. Now I am showing the pulses across this secondary of the transformer. Alright, now you can check here the pulses of the transformer. You can, I think, yeah, I hope it's visible, like thin lines you are able to see, right? This thin lines, whatever you are seeing is the firing pulses. Okay, thin lines, whatever you are seeing is these thin lines are the firing pulses. Okay, this pulses comes whenever the capacitor discharges. Now let's look back at the waveforms what we have in the manual. Let's compare it. Okay. Now when you look at the waveforms, we have seen the sinusoidal AC supply, then we have seen the rectifier output voltage. In your graph sheet, first graph you have to draw all these things. First you have to draw sinusoidal supply, then rectified output voltage whose peak value is 300 volts, and x-axis you have to take in degrees. Okay, each half cycle covers 180 degree. Choose scale accordingly. You can take 1 centimeter equal to 45 degrees. You can take 1 centimeter equal to 90 degree. It's your wish. Okay, I want you to draw waveform and x-axis to be in degrees. Then this waveform is the Zener output voltage we have seen. Then this waveform is the capacitor charging and discharging. This is the peak point. and this is the valley point, and whenever the capacitor discharges, that pulses are obtained across G1 and K1. Okay, now we have seen all these waveforms. I want you to draw all these waveforms in the graph sheet. Now let's start with the connections of half-wave rectifier circuit. First, we have given the supply connections as it is. From positive of supply, we are connecting it to anode of SCR. From anode, we are going it to load. Cathode. From cathode, we are giving it to load 1 terminal. From cathode, we are giving to one terminal of load, and other terminal of load is coming back to supply. Okay, this is a very simple circuit. What we have? We have 230 volts supply connected across the rectifier here. Now from positive of supply, we are connecting to anode. From negative, it's going to load. From load, it's coming back to negative of supply. Now we need to give gate and cathode connections. This G1 K1 should be connected to G1 K1 of this circuit. Okay, this is very important. Whenever you are doing connections, G1 to be connected to G1, G2 to be connected to G2. You are not supposed to interchange G1, G2, G3, all those things. Okay, according to notations, you have to give the connections. G1 to G1, K1 to K1. Right. This is a very simple circuit. We can see it in the manual here. Right. We have supply, AB terminals. This AB is nothing but your supply terminals, positive and negative of the supply, are red and black of your supply. Red you can take as A, black you can take as B. So from A, it is going to anode of SCR. From cathode, it is going to load 1 terminal. From load other terminal, it's coming back to supply. Same connections we have given here. From supply, it's going to anode. From cathode, it's going to load. From load, it's going back to supply. G1 is connected to G1, K1 is connected to K1. Now what we are going to see here is, we are going to observe the waveforms across SCR and load. Okay, in your manual you can observe, we have given the waveforms for some value of alpha. Okay, this is the voltage across SCR, this is voltage across load. Okay, now let's observe these waveforms in the CRO and let's understand how to vary the alpha and how to note down the value of alpha. Now let's connect it across the, let's switch on the supply. Let's switch on the supply. Okay, now let's switch on the supply. Okay, when you switch on the supply, the load will, or the bulb will glow. That's the indication that your circuit connections are proper and the waveforms whatever you are going to get is proper. Okay, you can observe here, as the alpha value varies, the output voltage will, when alpha is nearing to 0, output voltage is maximum. So when alpha is nearing to 0, the output voltage is maximum, indicating the maximum brightness of the bulb. When the resistance value is maximum, alpha will be nearing to 180 degree and the bulb glow will be less, or the illumination will be less. Let's check the waveforms at some value of alpha. Let's connect it across SCR first. Okay, the CRO probe connections I have connected across SCR. Okay, it's connected across SCR and it is channel 1. Now let's reduce the scale and I have kept it at 5 milliseconds. Okay, the scale I have kept it at 5 milliseconds and this is the waveform across SCR. Okay, what you can understand by looking at this waveform is, see, during this duration, this duration, the SCR is in off state. When SCR is in off state, voltage will appear across SCR. At this point, I am going to give the firing pulse. So the SCR turned on. So the voltage across SCR goes to 0. Now as I vary alpha, I am varying this potentiometer knob. As a result, the alpha is varying. As a result, the alpha is varying. Okay, until you give alpha, till that point SCR is in off state, voltage is appearing across SCR. Once you give firing angle, the voltage across SCR is going to 0. Okay, this is your second graph what you are going to draw in your graph for this experiment. First draw the sinusoidal supply, then for any value of alpha you have to draw this output voltage. The peak value remains same, 300 volts. For any value of alpha, let's say 90 degree, you have to draw this waveform. Now let's check the voltage waveform across load. So let's change the CRO probe across load. Okay, now I have connected it across load. So across load you are going to get waveform like this. Across load you are going to get waveform like this. Okay, the scale is at 5 millisecond, and how to make it out is, let me keep the alpha to 0. Okay, since it is an analog circuit, we won't get precise value of alpha. Okay, we will get approximate value of alpha. If you observe here, we all know that for a positive half cycle, the number of angle is the complete cycle covers 360 degree, positive half cycle cover 180 degree, negative half cycle covers 180 degree. Okay, if you can see here, this is the positive half cycle which is rectified output. The negative half cycle is not rectified, so the output voltage is 0. So these two divisions are covering positive half cycle, indicating 180 degrees. So each division is for 90 degrees. This division is 90 degrees, this division is 90 degree. If each division is 90 degree, one small division what we have here indicates 18 degrees. Right, one small division what we have here indicates 18 degree. So now I am setting the alpha, I am varying the resistance knob and I am setting the alpha to 18 degree. Okay, I am setting the alpha to 18 degree. You can observe here this 0 portion, this is the starting point. Okay, this is the starting point of your alpha. This is the starting point of the positive half cycle, and the 0 voltage is appearing till the first point. It indicates the load voltage is 0 between 0 to 18 degree, indicating the load is disconnected from load till 18 degree. So if I vary this and if I set it to 2 small divisions like this, it indicates till this point I have not given any firing angle, so the output voltage is 0. From this point I have given the firing angle. So this is how you measure the firing angle in 2 divisions by keeping time scale at 5 milliseconds. Okay, if whatever the duration, the output voltage is showing 0 in this 2 divisions, that's going to be your alpha. Now I am setting alpha to 45 degrees. Sorry, 90 degree. I'll set alpha to 90 degree. Okay, now the one complete division is 0. One complete division I am getting the output voltage. This indicates alpha equal to 90. Okay, this is how we can vary the alpha and we can draw the output voltage for different values of alpha. Okay, this is what we are supposed to do in this experiment. First thing, we need to do the connections, then vary the value of resistance at any different 2 values of alpha, observe the waveforms across SCR and load, note down it from CRO, draw it in your graph sheet. The third thing what we are going to do is, we are going to measure the output voltage. Okay, it's a controlled rectifier, right? The circuit connection what we have done is half wave controlled rectifier. Now I am interested in understanding what value of voltage I will get at the output side for what value of alpha, or as I vary alpha, how the output voltage is going to vary is my interest. So what I do is I set alpha first by looking at the waveform. By looking at the waveform, I will set alpha to 18 or 36 or 45 or 90. Then for the same value of alpha, I will measure the voltage across load. Okay, you can remove the probe terminals. Now I had set the alpha to 90 degree, and using the multimeter I can measure the voltage across load using multimeter. Multimeter should be kept in DC mode because the rectifier output is DC. Rectifier converts AC to DC, so the rectifier output is DC. So I am getting 59.6 at 90 degree alpha. Now I am varying alpha. Now I am reducing alpha nearing to 0. So this is the maximum voltage what I get. See, the illumination is bright and I have kept the resistance position to minimum position. So alpha is nearing to 0. The maximum output voltage what I get is 103. If I increase the value of alpha, the output voltage keeps on reducing. Okay, you can repeat this video and you can note down the values. This is for different values of alpha. As alpha decreases, the output voltage decreases. As alpha moves from 0 to 180 degree, the output voltage decreases. When alpha moves from 180 to 0, the output voltage increases. Okay, like that for different values of alpha, we need to note down VDC, and you have to plot the graph alpha versus DC. Okay, it's given in the procedure. You can check plot alpha versus VDC for practical values. Okay, now alpha SCR ಇಂದನು ನೋಡಬಹುದು. Okay, you can also check alpha from SCR. In SCR, if you check, see, I have kept alpha at 90 degree. What it indicates, your positive cycle is covering 180 degree. Until 90 degree, the voltage is appearing across SCR, indicating it is in off state. At this point, SCR is going to on state. That means this is the point at which I have given firing angle to SCR. So this complete duration with reference to this point, with reference to zero crossing of positive half cycle, till this point is your alpha. So this period is your alpha. Okay, in this case, okay, this entire period is your alpha, and each small division is 18 degrees when your time scale is kept at 5 milliseconds. Okay, this is how you need to note down the waveforms and readings. You have a tabular column given in the manual. You can skip these two steps. You can directly note down the value of alpha, VDC practical. Then you need to calculate the theoretical value using the formula given below. Then you need to plot graph alpha versus VDC. Okay, this is about single phase half controlled rectifier using UJT relaxation oscillator. Okay, now let's see how to conduct full wave rectifier. Okay, this is the circuit diagram for full wave rectifier of UJT relaxation oscillator. If you observe here, the supply 230 volts is given to rectifier terminals, and the output of rectifier is connected to half wave control rectifier. Okay, the remaining part of the circuit is similar to half wave rectifier. Instead of giving AC supply, we have given rectified output voltage. Okay, the rectified output voltage waveform looks like this. So in each and every time when this pulse appears across SCR, it turns on. So if you take this as alpha, this will turn on at this point. Again in the next cycle, it will turn on at this point. So the output looks like full wave rectifier. Okay, that's what we are done in the connections here. I have removed the connections across these 2 points, and we have connected across these 2 points. Okay, from anode, the connection is going to the rectifier output terminal, and from cathode it's going to load. Then from load it's going to rectifier one more output terminal. Okay, now the procedure is same as we did for half controlled rectifier. Now we need to observe the waveforms across SCR and load. You need to draw the waveforms for different values of alpha across SCR and load. Okay, now I have connected the probe across SCR. You can observe here, this is the waveform across SCR. Now let me vary the value of R. Okay, this is for alpha equal to 0. For alpha equal to 0 means here we will get 18 degree. For alpha equal to 18 degree, the output voltage, the voltage across SCR is like this. If you increase the value of alpha, the voltage across SCR will be like this. Okay, you have to note the value of alpha, and then let's see the waveforms across load. Okay, let's connect the probe across load. Across load, this is the waveform across load. Okay, you need to measure alpha same way. Okay, this is for alpha equal to 18 degree, this is for alpha equal to 90 degree, and this is for some alpha greater than 90 degree. Like this, for any 2 points of alpha, you need to draw the waveforms across SCR and load. Then for each and every value of alpha, you need to measure voltage across load. You need to measure voltage across load using multimeter by keeping it in DC mode. Okay, now as you vary the voltage alpha, the voltage across load increases. Okay, you can observe here, since it is a full wave rectifier, when alpha is equal to 18 degree, the output voltage is 203.6. In the previous case, it is 101 something. So since we are rectifying both the half cycles, in this case, the output voltage is more. Okay, as you increase the value of alpha, the output voltage keeps on decreasing. Okay, you have to plot the graph between VDC versus alpha, and then you have to plot the waveforms across SCR and load. Okay, this is all about the conduction of full wave rectifier of UJT relaxation oscillator.